The theme for this year's TEDxChamonix event is breakthrough. And I want to facilitate for you a breakthrough moment in your understanding of mathematical probability and statistics. Before I do that, could I get a show of hands of how many people in this room don't believe that they have a mathematical brain? Cool. I'm going to prove you wrong. For the rest of you, I'm going to prove you can be stronger than you are right now. Everyone has the capacity to understand mathematics. It is instinctive. It is the thread that is woven into the fabric of how we reason. It is inherent in all human beings, and you can cultivate your mathematical brain. Let me give you a quick example to show you how powerful a tool your mathematical brain really is. Consider the number 5. I bet almost everyone in this room knows what 5 squared. What's 5 squared? 5 times 5? 25. There we go. How about 25 squared? Who knows what 25 squared is? For those of you I barely heard, you're out there. Yes, it is 625. For the rest of you, you tried to push your brain to follow a complicated algorithm that you learned in school. Your heart rate increased, your pupils dilated, and the whole while you tried to hold certain combinations in your head. You either reached a conclusion or you gave up. In either case, I'm happy to report heart rates are coming back down, pupils are now normalized for the lighting in this room. So let's find the square of any number ending in 5. Let's go back to our 25 squared. All I want you to do is hold the first digit in your head, the 2. Now multiply 2 by 1 more than 2. 2 times 3. 2 times 3 is 6. 5 squared is still 25. The answer is 625. Let's try it for 35 squared. What's 35 squared? Same technique. I hold the 3 in my head. I multiply 3 by 1 more than 3. 3 times 4 is 12. 5 squared is 25. The answer is 1225. For the rest of you still going on, yes, 45 squared is indeed 2025. But take a moment and look what just happened here. In less than 2 minutes, you learned a completely new mathematical algorithm. And we had fun. But why is it important that we cultivate our mathematical brain? Because maths is what underpins our whole world. We're living in an age of unprecedented information overload. Online news sources are huge information streams that have come to heavily influence our lives. There is more news, data, and information that we are being subjected to. And with this increase in information and ideas, there are more mathematical probability and statistics statements being made about everything, from physics to medicine, investment banking, trading, public health, political polling, climate science, your Facebook feed. It's everywhere. The gap between the hard sciences and soft sciences is shrinking. And it's shrinking because of an increased use of probability and statistics. So how can we process all of this? Before I answer that question, I want to clear up a common misconception. Probability theory seeks to understand randomness. It isn't itself random. As a field of study, it provides us with mathematical theorems that allow us to follow a very precise mathematical course to a conclusion. Statistics, on the other hand, summarizes, using mathematical techniques, data that is produced by experiments or phenomenon. And that data, or those experiments, have an underlying element of randomness to them. You can think of them like a before and after picture. Probability is the before, statistics is the after. So let's get back to that question. How do we process all of this information? I want to introduce you today to 3 key concepts that I think you can use to critically arm yourselves to think about what mathematical probability and statistics say about the real world, so that you'll be more comfortable understanding the information that's being presented, more empowered to challenge or question it, and better equipped to make your own choices and decisions with regards to it. The first idea I want to highlight is small sample size. We need to guard ourselves against drawing conclusions that are not warranted or supported by the data. This example went viral. From science journals to the popular press, thousands of Facebook shares and tweets. The title, "Pregnancy Sculpts Women's Brains for at least 2 years." A first of its kind study has shown that the architecture of women's brains changes strikingly during their first pregnancies and in ways that last 2 years. This title was tweeted I don't know how many times. Hashtag pregnancy makes you lose your mind. But let's take a look at the content. The researchers showed that for these first-time mothers, they had gray matter volume loss that persisted and could be shown to still exist 2 years later. Let's look at the data. The MRI scans of 25 women were performed, both before pregnancy and after pregnancy. MRI scans of 20 other women were also performed. They didn't get pregnant. Let's take that in for a minute. 25 women showed gray matter volume loss, and 25 other women showed no gray matter volume loss. If I'm reading the crowd correctly, your reaction when I showed you that small sample size was the same as mine. Your mathematical brain and my mathematical brain instinctively raised a red flag, and we said, hang on a second here. There's two things that were happening. The first is that collectively, we realized we could not possibly extrapolate these conclusions from a sample size of 25 to the population at large. But the second thing, equally justifiable, was that, hang on a second moment, 25 women did show gray matter volume loss. There might actually be something here. And in fairness, that is all the researchers claimed. There might be something here. Exciting research should go forward. Once presented with this information, together, we all came to conclusions that are in fact warranted by the data. And interestingly enough, the same conclusions that the researchers came to. This is a fun example. And it's interesting and further exciting research will go forward. Nobody got hurt. This has not always been the case, most notably in the medical sciences. There have been many examples where small sample sizes have led to treatments being prescribed that were later contradicted by larger, significantly larger studies. An example I want to highlight today is hormone therapy in postmenopausal women for heart health. The original study contained 875 women. Several years later, two large studies, an aggregate of about 42,000 women, were performed. And these second studies contradicted the initial studies that hormone therapy was beneficial in postmenopausal women for heart health. They didn't minimize them. They contradicted them. Before these larger and later studies were conducted, over 105 million women in the United States alone were prescribed hormone therapy for heart health. And that hormone therapy, in fact, increased their risk of coronary artery disease. Sample size matters. Replication matters. Second idea I want to highlight today is about independence. 2016 was the year of celebrity deaths. All the major news sources were reporting either a significant death curse or an uptake in celebrity deaths. Eventually, they came to a question, which was posed in the popular media: were there more celebrity deaths in 2016 than should be expected. This is actually a mathematically formulated question. We can analyze this, and it was. A statistical analysis was performed and printed in the popular press. But here's the thing. When we attempt to make sense of uncertainty, and we reach for those tools of statistics, we have to take care not to gloss over one of the most important assumptions that is at the basis of every single common statistical technique. Suppose these events are independent. So when I read this statistical analysis, a little alarm went off in my brain. Because while deaths are independent, I could not quite convince myself that the deaths of Debbie Reynolds and Carrie Fisher, a mother and daughter, within 24 hours of each other, could be independent events. But let's go back to the question that was circulating in the news. Were there more celebrity deaths than should be expected in 2016? It was like, collectively, We Are the World was trying to weigh the likelihood that these deaths could be linked, caused by some sort of shared event or experience. The mathematical instinct kicked in. That is a mathematical formulated question. So the next time you read a sensational news headline, ask yourself, are these events independent? And now the last one, confidence intervals. And this is a big one, especially in our political climate. We often see confidence intervals in the context of election poll statistics or electoral predictions. For example, the number of, the percentage of votes that a given candidate will win. When we hear Emmanuel Macron is predicted to win 62% of the popular vote, how do we interpret that? Inherent in that statement is that there is a plus or minus 5% points of a margin of error. That means that the true percentage of votes that Emmanuel Macron will win, lives in the interval 57% of the votes to 67% of the votes with 95% confidence. It also means that 5% of the time, the true value of the percentage of votes that Emmanuel Macron will win does not even lie in this interval. And we're making no statement of where it does live. Let me give you a second example of confidence intervals, again in an election context. The Brexit vote. In 2016, the UK held a referendum to decide whether or not to leave or stay in the European Union, the Brexit vote. Going into the vote, 48% of surveyed voters indicated that they had the intent to vote to stay. 46% that they had the intent to vote to leave, and 6% were undecided. To make a quick point here, historically, in the United Kingdom, on average, their margins of error are 6 points. We just got to go with it. They're special. Okay? So let's take a look at the Brexit results the same way we looked at the French election results. Let's start with the stay vote. 48% was the predicted percentage. That means the true value of the percentage of votes that will come in for stay lives in the interval 42 to 54%. Let's look at the leave percentage. 46% was the reported prediction. The true value of the percentage of votes that will come in for leave lives in the interval 40 to 52%. First thing to notice is that these confidence intervals overlap. Probabilistically speaking, the vote could go either way. The outcome was 48% to 52%, 52% to leave. Many people were shocked by these results, but you shouldn't be. Going into the vote, the probability of the leave vote lived in the interval 40 to 52%, with 95% confidence. What can we learn from this? Exit poll statistics live in an interval. Plus or minus 5 points for most of the world, plus or minus 6 points for the UK. Secondly, 5% of the time, 1 in 20 times, we don't know where they are anyway. They're outside of that interval. That way, when the headline comes up, it won't be shocking to you. You'll have realized that these results had a probability of occurring all along. We're waking up these days to news that is designed to shock us. We tout extreme values. Trump, Brexit, the financial crisis. But these events are neither extreme nor outliers. They had a high probability of occurring all along. So where are we now? Where I hope we are is that it's not just dawning on you that you are instinctively mathematical, but I've got you to a point that there's a conviction that you are instinctively mathematical. More than that, I hope you're inspired to cultivate your mathematical brain, to have fun with it, and to critically think about what mathematical probabilities and statistics say about our 21st century reality. From everything of medical breakthroughs to natural disasters, from election results to avalanche data. You can evaluate the likelihood of these events and make your own decisions with regards to it. You are mathematical. Thank you.